All right, so 2.5 power rule. Now, I'm going to tell you what the derivative of these functions are. Again, you may already know the power rule. If you do, great. But if you don't, you should be able to kind of grasp the power rule by looking at the pattern. So for the first one, the derivative is 2, helps if I write, 2x. Second one is 3x squared. Third one is 4x cubed. And the fifth one is 5x to the fourth. So if you have forgotten the power rule, what is the pattern that has emerged? Okay. Specifically, let's look at what the exponent was and what it is and what happened to the exponent. Yep. The exponent decreased by 1 each time, but also the exponent became what? The coefficient. That is the power rule. You bring the exponent down, subtract 1 from the exponent, and that's it. So, which means, if you remember, I'm going to go back here to these notes previous. So if you remember doing this question here, number 3, all that work we did for number 3 just to find the derivative, if I do the power rule for that, what do I get? 4x. Do the power rule for that. Now, again, because it's a 1, if you subtract 1 from 1, that's just going to go away, right? And if you remember the notes, what was our derivative function? 4x minus 7. So instead of doing all that limit as h approaches 0 from f of x plus h minus f of x over h, and then rationalizing and all that fun stuff, you could just use the power rule. Same with number 4. If we write that as x to the negative 2 first, we're going to bring down that negative 2 and then subtract 1. So it goes down, subtract 1, x to the negative 3, which is what we got, negative 2 over x cubed. So again, this is the shortcut day. So all we're doing today is just a bunch of ways to make finding the derivative easier and faster. So that is our power rule. So what would be the derivative of x to the 37th? 37x to the 36th. All right, so y prime is equal to that. What about x to the 9th? Well, dy dx is equal to 9x to the 8th. I'm going to go back and forth between dy dx and y prime just so you're comfortable with both. Okay, just note they do mean the same thing. I also use f prime of x sometimes. They all mean the same thing. I just want to make sure you're comfortable with them. There are some instances where we have to use the Leibniz notation of dy dx. So I want to make sure you're familiar with it before we really get into those. So now some questions it might be easier to rewrite. And we kind of already seen an example of that when I went back up and redid that previous question. We can rewrite any term that has a variable in the denominator, just a single variable in the denominator with a negative exponent. So y is equal to x to the negative 1. All right. Then we do the power rule. So we're going to bring down, so y prime is equal to negative 1 x, and we're going to subtract 1 from the exponent. Negative 1 minus 1 is negative 2. And again, if necessary, because it may not always be necessary, I usually don't care if you leave a negative exponent. So that would be fine for me. But again, if you're doing a multiple choice question, you do need to be able to make sure you put it back as f prime of x. And I'll just go back and forth here. Negative 1 over x squared. All right. So we have y is equal to x to the negative 4th. So dy dx is equal to negative 4x to the negative 5th. So y prime is equal to negative 4 over x to the 5th. Now, the real fun times come with rational exponents. Right? So we write rational exponents as, in this case, 1x to the 1/2. So we're going to bring down, so y prime equals 1/2. If I subtract 1 from that, I get negative 1/2. So dy dx is equal to 1 over 2 squared of x. All right. So for number 6, y is equal to x to the 3/7. We're going to bring down 3/7. Subtract 1 from 3/7. Again, just my subtracting 7/7. So we get negative 4 over 7. So we get dy dx equal to 3 over 7, 7th root of x to the 4th. It's kind of hard to read. Let me write that better. 7th root of x to the 4th. There we go. And again, personally, on a test, if you're writing this freehand, if you're doing a pre-response question, I'd be perfectly fine you leaving it as x to the negative 4/7 because it makes no difference. It's still correct. The only reason I rewrite is just in case word multiple choice questions, you don't have a choice in how they represent them. All right. So now we can simplify number 7. Okay. So first thing first, we are going to rewrite this as f of x is equal to x to the 1 over x to the 1/2. All right, and since with division you subtract exponents, we just get x to the 1/2. So f prime of x means we're going to bring down that 1/2, subtract 1 from the exponent, so just bring down and subtract 1, so x to the negative 1/2. Okay, or 1 over 2 squared of x, which means f prime of 7 is 1 over 2 root 7. So we have f of x is equal to x to the 1/3 times x to the 3, which gives you x to the 10/3. If you add those together, 3 1/3 is 10/3. So f prime of x would be 10/3. And when you're subtracting 1, again, we're going to bring that down and subtract 1. I'm going to subtract 3 over 3, which gives you 7/3. So f prime of 8 would be 10/3 times, I'm going to do the cube root of 8 to the 7th. Doesn't matter if that 7 is inside or outside. Honestly, it's just easier to put it outside at this time. So you can cube root first and then raise to the 7th power. The order of that is not important. So the cube root of 8 is 2, and 2 to the 7th power is 128. So we get 10 times 128, or 1280 over 3. All right. So parallel tangent lines. Let f of x be x to the fourth and g of x be x cubed. At what values of x do the graphs of g and f have parallel tangent lines? Which basically means when will their derivatives be equal? Okay. So when is f prime of x equal to g prime of x? That's the question. Now f prime of x, easy enough. Bring down the 4, subtract 1 for x cubed. When is that equal to? Bring down the 3, subtract 1 from the exponent, 3x squared. So subtract 3x squared over. 4x cubed minus 3x squared is equal to 0. Factor out the x squared, for x minus 3 equals 0. And there's two values for x. X equals 0 and 3/4. So those are the two values where the derivatives will be equal, which means they will have parallel tangent lines. That is it for the first of the three to go. Fortunately enough, these are pretty easy. All right. Now, we are going to still do some of these power rules, but what we've done so far is just monomials. Okay, what happens if we have polynomials? Well, we're going to talk about several different rules for derivatives. First of all, what is the derivative of a constant? Okay, and remember, you have to think, what is derivative finding? It's finding the slope of the function, the slope of the line. And if you have a constant function, what is the linear form of a constant function? Graphically, it's a horizontal line, right? What's the slope of a horizontal line? 0. So the derivative of every constant will always be what? 0. Right? Now, this is where we're going to use that Leibniz notation, because we're taking the derivative of x of cu. Now, u is a function. Okay, u is just a function. It's like we could write u of x, okay, but we didn't want to write u of x, okay? It's like saying y there. It's just a function, all right? So when we take the derivative with a constant, the constant is going to go outside the derivative, and this becomes c times du dx. All right. Example of that would be if I had y is equal to 3x squared. When we bring down that exponent, we're going to multiply it. So that's going to become y prime is equal to 6x. So if we have a constant outside, we just bring it out, do the derivative, and then multiply it back in. If we have more than just a monomial, we can distribute a derivative just like we can with a limit function. We can distribute it through the function itself. So this will become du dx plus or minus dv dx. And again, all that says is we're going to take the derivative according to x for both of those separate values. So again, an example of that would be if we had something like y is equal to 5x to the fourth plus 2x cubed. All right, we're just going to do the derivative of them separately. So y prime, bring down the 4. 4 times 5 is 20. Subtract 1, 20x cubed. Plus, bring down the 3. 3 times 2 is 6. Subtract 1, x squared. We just take the derivative of them separately. All right. So, here we have y equals 2x squared minus 5 over x. Again, I would probably write that as 2x squared minus 5x to the 1 plus 6, x to the negative 1, sorry, plus 6. Then take the derivative of each of those separately. So what is the derivative of 2x squared? 4x. What is the derivative of 5x to the negative 1? Now, when you bring down that negative 1, what's going to happen to this negative? Positive 5x to the negative 2. Derivative of a constant is 0, so we just drop it. Now, if you want to rewrite it, again, I don't care if you do, 4x plus 5 over x squared. Again, not super necessary, but you can. Oh, y prime. All right, so number 2, again, rewrite this as 8x to the 1/2 minus 1/3 x to the 6th plus 2 pi to the 5th. Now that 2 pi to the 5th is just to throw you off. Pi is still a constant. Even though it's an irrational constant, it's still a constant. What's the derivative of any constant? 0. So when you do the derivative of this, that 2 pi to the constant is just going, or 2 pi to the 5th is just going to become 0, no matter if it has an exponent or not. It makes no difference. But that will tend to trip people up. Okay, just because it has an exponent, I'm going to see 10 pi to the 4th sometimes. Okay, don't let that be you. So yeah, that will just go away. So dy dx, bring down the 1/2. 8 times 1/2 is 4. Subtract 1, negative 1/2. Bring down the 6. 1/3 of 6 is 2. Subtract 1. And again, that's just a constant, so it goes away. And again, you could write that as 4 over square root of x minus 2x to the 5th. Now, one of the things we are going to do quite often, especially in the later chapters, what it calls applications of differentiation, is you've talked about local max and local mins, right? Well, where is a local max? Graphically speaking, where is a local max or local min? Like for over here, all right, where's your local max? Well, it's right here. That is a local max. All right, local min, local minimum. What is the slope of the tangent line for both of those? If I were to draw a tangent line there, what would it look like? Yeah, they'd be horizontal lines. And in order to have a slope that is a horizontal line, what would the slope's value be? 0. So we can use derivatives to find local max and local mins by taking the derivative function and setting it equal to 0. Now, will it tell us if it's a local max or local min? No, it'll just tell us there's a turning point here. Okay, we'd have to plug it in to see if it's a local max or local min. So we are going to find just the x values of any horizontal tangent lines. So we're going to first find f prime of x. So what's the derivative of this function? 8x plus 7. So if we set that equal to 0, equals 8x plus 7, what does x have to be? Negative 7 over 8. That is your x value of the horizontal tangent line. By the way, this is not the graph of that function, obviously, because that's a quadratic function. That's at least a cubic function, if not more. All right. Let me know what a normal line is, outside of just reading what it says here. All right. A normal line is goes to the same point as a tangent line, but is perpendicular to the tangent line. Okay. So what we're going to do is we are going to find the tangent line first, the slope of the tangent line, and then we're just going to invert it like you would if you want to find a perpendicular line based upon this slope. you would do the negative reciprocal and then write your equation. So, find the equation of the normal line of this function, and this is actually the graph, so this is actually the coordinate right here. All right. Now, the reason why that's important is what's the y value? -3. So we have that. We just need the slope now. Now, to find the slope, we need to find f prime of 3. So first, f prime of x. Derivative of x, going to bring down 3. Subtract 1. Bring down 2. Subtract 1. And then again, anything just x becomes a constant, so plus 1. So there's your derivative. Now, f prime of 3 means that we get 3 times 3 squared minus 3 times 4 plus 1, which is 27 minus 24 plus 1, which is 4. Now that is the slope of the tangent line. What's the negative reciprocal? -1/4. So again, just put this in point slope form. Y minus the y value, which is -3, so plus 3, is equal to -1/4 times x minus the x value. And that's it. There's your equation. You are not going to get a lot of questions that are going to tell you to put this in slope-intercept form. So you're going to need to get pretty comfortable with point-slope form. All right. Now, differentiability with piecewise function. Right. First thing we need to do, again, in order to be differentiable, what does it have to be? It has to be continuous. So we do have to check for continuity, because if it's not continuous, we just say not differentiable and that's it. Okay. So first one, check for continuity. So plug in -1, 5 times -1 squared plus 3 times -1 plus 2. Does that equal -7 times -1 minus 3? So does 5 minus 3 plus 2 equal to 7 minus 3? So does 4 equal 4? Yeah, it is continuous. So we're good there. All right. Now, if it is continuous, a piecewise function is only differentiable if the derivatives also meet at the same value. Okay. So we are going to first take the derivatives. F prime of x would be what? 10x plus 3 and -7, where x is less than -1, x is greater than or equal to -1. So does 10 times -1 plus 3 equal -7? Yeah. -7 is equal to -7. So yes, it is differentiable. All right. What values of a and b would make the function f of x equal this and be differentiable at 3? So first of all, it needs to be continuous at 3. So we're going to do the check for show, well, what values we need for it to be continuous at 3. So we have 3 squared minus a times 3 plus 2 has to equal 3 plus b. All right. So that means 9 minus 3a plus 2 equals 3 plus b. So 11 minus 3a equals b. And we could, oh wait, I forgot the 3 plus b. It's b. So b is equal to 8 minus 3a. That has to be true. Or to be continuous, that has to be true. All right, next we are going to take the derivative, so f prime of x. Now, b is a constant, so when we do the derivative of that second part, it's just going to be 1. So first we have, 2x minus a when x is less than 3, or 1 when x is greater than or equal to 3. So these have to be equal. So 2x now, and then at 3. So 2 times 3 minus a has to equal 1. So 6 minus a equals 1, which means a is equal to 5. Now if a is equal to 5, we can plug that back in here. B is equal to 8 minus 3 times 5. B is equal to 8 minus 15. B equals negative 7. And there we go. Any questions on the first two? 0.5, 2.6? All right. Now, this is going to take just memorization. You are going to need to know what the derivative cosine is, derivative sine is. There is a really, really long proof that goes to proving why the derivative sine is cosine. It does even involve the squeeze theorem, which is fun. So, I don't want to do that because 1, we don't have time for it, and 2, it's unnecessary. Just know that if you're ever asked derivative sine, it is cosine. All right? Just memorize that. Derivative of cosine is negative sine. Now, here's a little hint that's going to come up later on. If the trig function starts with a c, then its derivative is negative, which means the derivative of cotangent and cosecant will also both be negative, but secant and tangent will not be. That's just a pattern comes up. It does make it easier when you're trying to think about what signs you need, like is it positive or negative? Well, if it started with a c, its derivative will be negative. If it didn't start with a c, its derivative will be positive. So, find examples of, for example 1, find f prime of this function. And again, we can just do this separately. What's the derivative of sine? Cosine. So 2 cosine x. Derivative of cosine is negative sine, so that's going to become a positive 5 sine x. And that's all you do. That's it. It's just going to be memorization. You just have to know it. Okay? Now, what is the natural log of 1? 0. Natural log of 0 does not exist, or it's undefined. E to the 0 is 1. E natural log of a is a, and natural log of e to the a is also a. So, this is also something you're going to need to memorize. Derivative of an exponential function. Derivative of an exponential function will always be itself times the natural log of the base. The derivative of an exponential function will always be itself times the natural log of the base. Which means if we take the derivative of e to the x, that is going to be e to the x times the natural log of e. But what is the natural log of e? 1. So this just becomes e to the x. This is one of the few functions where the function is its own derivative. So the derivative of e to the x is e to the x. So, What is the derivative of 2 to the x? Well, again, it's itself. So f prime of x is itself 2 to the x times natural log of 2. Plus derivative of 3e to the x would be 3e to the x. It's its own derivative. So, yeah, that's it. Now, derivatives of log functions are very similar to exponential functions. Okay, they're always going to be the same thing times a natural log of the base. Okay, but it's a little bit different. Derivative of a log base a of x is 1 over x times 1 over the natural log of a. Now, since natural log is log base e, this is 1 over x times the natural log, 1 over natural log of e, which is still just 1. So we just get 1 over x. So the derivative of a natural log of x is always just 1 over x. It's when you have different bases that you're going to have to include that log base a. Now, usually we would write this as just 1 over x log base a as one fraction. Not that you could see that because that's really weird. So 1 over x natural log of a, all is one fraction. Still not much better, but still. So with that in mind, the derivative of natural log of 4 of x is 1 over x natural log of 4. Minus 4 times natural log of x, which is minus 4 over x. The coefficient just stays in the numerator. So these are going to be things you need to just memorize. And one way to memorize that is to practice it. So, what is the derivative of number 1? You guys spend some time on 1, 2, and 3. Go ahead and answer those, and then I'll go through them. All right. About all the time you really need for these. So derivative of 2 sine x is 2 cosine x. Derivative of 5e to the x is just 5e to the x. That's it. Number 2, dy dx. 3 to the power of x is 3 to the power of x, natural log of 3, plus 4 sine x. And number 3, f prime of x is 1 over x, natural log of 2, minus cosine x. There you go. Next page. Yep, a couple more. Now here they want us to plug in 5. We do not have to simplify. It's like when we get down here, you'll see we can a little bit, but not everything's going to be something I want to find an absolute value for. So first, f prime of x first. Derivative of 3 natural log of x is 3 over x. Derivative of e to the x is just e to the x. Means f prime of 5 would be 3 over 5 plus e to the 5th. You do not have to take that further. That is fine. Do not give me a decimal value unless it says round to the nearest whatever. Just leave it as it is. So for number 5, first f prime of x is equal to negative 3 sine x. All right, plus 1/2 cosine x. So f prime of pi is negative 3 sine of pi plus 1/2 cosine of pi. Now sine of pi is what? 0. Cosine of pi is negative 1. Right? Which means this gives you what? Yep, negative 1/2. And that is it for the notes today.